Hey guys, Mr. Riz here to help you walk through the how to survive a zombie attack. So this is a theoretical thing, so this didn't happen, but we're going to pretend like in June 30th in 2035. So in a couple of years, a sleeper cell of zombies executed an evil plan 10 years in the making. So their objective was to turn the entire human race into evil zombies, not just like good zombies, but evil zombies. All right, each zombie can turn 3 humans per day, but they are not sure how long it would take completely to turn every human on the planet. So we're going to complete this table below to help them out because they need brains. And we're going to look at the first 10 days of the attack. So the original sleeper cell only had 5 members, and so day 0 has 5. But keep in mind that every newly turned zombie will also have the power, and he will turn the other ones to turn other humans. So let's start going through this pattern or start filling this out. So let's see, if on day 1 we have 5 zombies, what we can do here is to take each 5 can turn 3 more. So that'd be 5 times 3 is 15, and then plus the original 5. And so that means we would have a total of 20 zombies. And what we're going to do is every single one of these actually should not be the zombie. Let's do the total number of zombies. It's going to actually make our math a little bit more accurate. Because when we try to figure out how much to take over the world, it would actually work out. Okay, so we got 20 total zombies that day. All right, so after day 1. Now day 2, we got 20 zombies. Each of them can turn 3, so that's 60 plus the 20 from the start of it. 60 turn plus the 20 original. Okay, we got 80 zombies. We'll just keep this pattern going. All right, 80 can turn 3 more. 80 times 3 is 240 plus our 80 original. All right, so that's 320. Hopefully right now, like pause if you can't, try to see if there's a pattern here. All right, so next 320, we times that by 3, which is a lot. It is 960, and we'd add our 320 to that, and we'd get 1280. Now, okay, do you see the pattern? I'll go from 5 to 20 to 80 to 320 to all right, we're basically timesing by 4. So if we times this by 4 here, we get 5,120. If we times that by 4, we got 20,480. If we times that by 4, 81,920. All right, let's keep timesing this by 4. All right, 327,680. We'll times that by 4. We got 1,310,720, and we'll times that by 4. So that means we got 5,242,880 zombies. All right, we're going to leave X there alone because we will eventually, throughout this work, figure out a formula to determine how many zombies there are per day. So what was the patterns that you notice in the growth of how many turn each day as they go by? So what's the pattern here? We kind of said it. They get multiplied by 4, right? Next, what we want to do here is to quickly kind of sketch out a graph. So we can use these as points here to help us out. Now, these points you can see, like even if you start out with like, let's see, 0, and we go by hundreds, 200, 300, 400, 500, 600, 700, 800, 900. We go all the way up to 1,000. You'll see it's going to start out real low. So at 0, there were 10, so barely off this. Or yeah, there was 10, right? All right, then we had 5, and then we had 20 on day 1, and then day 2 we had 80, and then day 3 we had what, 320? Okay, so that jumps out. That's a pretty big jump. 320 is probably right here, and then day 4, what do we have? We have to go back and look at the chart. Just use a calculator. We had 1280. So already off of the chart here. So it starts out super low and then boom, just explodes. All right. So this is a clear example of what we looked at yesterday called exponential growth. All right. So how many zombies were turned on day 10? What was that? I got to look this up. You guys look back at that. We had a total of 5,200. Okay. So next, what would you have to multiply this number to get how many were created on day 11? You know, right? We got to times that by 4, right? So how would the entire table change if we started out with 5, instead of 5 zombies, we started out with 1. Okay, so we still multiply, so we'd have 1 zombie on day 0. And then on day 1, okay, we'd have, well, actually, no, we'd have 4 plus the original, so we'd, okay, no, we'd have, then, you know, never mind, I'm thinking backwards. We'd have 4 zombies, because that guy would turn 3 plus himself, that'd be 4. All right, now on day 2, how about Z's and days here? How many days 2? Okay, that we'd have 16, and then 64, and then what's after that? 64 times 4. So 256, I should have known that. And we times that by 4. All right, and then we get 1024, and then we got 4096. Okay, you can still, it keeps growing up. The numbers aren't as big, but eventually it still gets to a point where it gets ridiculous. 16,384, 65,536, 262,000, 1 million. And so it doesn't take too long that we're in the millions and the 4 million. So it still goes up exponentially. All right, how long would it take the world to take over the world if we're looking for just about 7 billion? So use your calculator here, use whatever, and just keep track. Okay, if we have 5,280, in fact, you know what? I could probably pull up a calculator here. This might be more beneficial for you guys to see. All right, come on, pull up. Waiting for this to load. All right, let's clear this out. So if we got 5,242,880 on day 10, if we times that by 4, here's day 11. Times that by 4, there's day 12. Times that by 4, there's day 13. All right, here's day 14. Okay, so that's like 100 million, right? 15, 16. Okay, so now we're actually starting to get into the billions, right? So actually, no, what is this? 5? 1, 2, okay, so what is that? 15, so somewhere around that 16-day range, something like. Okay, which one of these equations? Here's the problem. This actually, I will give you the answer for this one. The equation that we would use to figure this out, and actually goes back to the end of our notes here, would be this one here if that was a 4. All right, so the answer, and we could get that because the equation is always A times the growth rate times T. So if we have this here, Y equals, we start out with the initial population of 5, and then we're timesing it by 4 to the X power. So on day 0, 4 to the 0 power is 1 times 5 is 5. All right, on day 1, we'd had 20 because 5 times 4 to the first, or just 5 times 4 is 20. And this pattern would work the whole way through. So what does this X variable represent in this problem? The X would represent how many days we would have. All right, next, write an equation. So instead of 12 zombies, we're in a sleeper cell initially and had the ability to infect 6 people per day. All right, so let's see how that would go through. You'd have to change this equation up just a little bit. It'd still be Y equals some number. Well, our 5 was how many zombies we started with. So we'd start with 12 zombies. And then our 4 was how many plus 1 that they could infect. So we can infect 3 zombies per day, or make 3 zombies per day plus the 1 original. So if we make 6 zombies per day, so that'd be 7, because we'd have 6 plus the 1 original to the X power. And how long would this take to take over the world? Well, we just kind of keep going through a pattern here. Okay, start with 12 and times it by 7 and keep going until you get the basically 7 billion that is in the world. All right, next you have this question here, and this question has no right or wrong answer, but if you were given the choice, which would you rather have, a slower growth rate with fewer initial zombies, or a greater growth rate, oh wait, let me say this again, said the backward. Would you rather have more initial zombies with a slower growth rate, so you start out with 100 zombies, but they only double each day, or would you have fewer initial zombies that have a slower growth rate? So, or a greater growth rate. So would you rather have like 2 zombies, but they multiply by 10 every day? Which one would you pick and why? You might want to be like, hey, well, at this one here, if we have a lower, or we might be able to curve the, what do we say now? Curve or bend the curve, flatten the curve to maybe initialize something. Or hey, you might want to get it over and done with quick, right? If we're all going to be zombies, let's do this fast. So decide. All right, next what we're going to do is look at decay. So within 3 days of the initial attacks being reported, a group of scientists quickly began working to find an antidote for the zombieism. Within a few short weeks, they were successful, but unfortunately, their antidote was found to only be successful 15% of the time. So we're going to make a table showing how many zombies were cured after 10 rounds of administering the antidote. And we're going to assume that every remaining zombie, given the antidote in every round, no new zombies are created. So we cut off the zombie and 15% of the zombies go away each time. So an easy way to think about this here is if we are going to be taking 15% away, and this is a trick to do. If we're going to take 15%, instead of multiplying this number by 0.15 and subtracting it, what we might want to do, if we're getting rid of 15%, that means we have 85% remaining. And so what we're going to do here, each one of these, we're going to times by 0.85. So we'll take out a calculator here and just start plugging in these numbers, and we'll times it by 0.85. And I got this calculator here to help me out. So we're going to start out with 6 billion, no, that's not a 6 billion, 975 million. We're going to times that by 0.85. So after day one, the first day, we got 5,928,750,000. All right, then we're going to times that by 0.85. All right, now we're down to just over 5 billion. All right, that's on day 2. Day 3, day 4, day 5, day 6. You guys can pause this video at any time to write these numbers in. Day 7, day 8, day 9, and after 10 days, there we go. We got still over 1 billion zombies in the world, but there we go. So if we notice here, some things about this decay pattern is that there's a cumulative amount. And so if we're kind of talking about, after each round, what would we have to multiply, or what is our remaining amount? And you think about it, if 15% of the zombies, how much would remain? Kind of set up there at the top, should be 85%. All right, so for problem 9, you're going to do a quick sketch of the graph, and you should probably see the graph kind of curves down. Now, you don't have to make a perfect graph with dots unless you want. There we go. All right, let me help you out with this next part here. If we want to do a decay problem, we always take our y equals our initial population times the rate over time. So our initial population was like that 6 billion, was it 975 million? Whole bunch of zeros. So there's our initial population. Now the growth rate isn't 2 for doubling. It isn't 4 for quadrupling. It isn't 0.15 for 15%. The growth rate is actually 0.85. So each time we're finding 85. So it's a 0.85 growth, which is kind of weird because it's not technically a growth, it's a decay to the x. So anytime we have a rate that is less than 1, it's a decay, and 0.85 is less than 1, so we have a decay. That should help us out. All right, next, how long will it take? So if we go back here, all right, this was day 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50. Geez, we're still got over 2 million. 1, 2, 3, 4, 5, 6, 7, 8, 9, 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, 80. Okay, so it's going to keep going on and on and on. Okay, will we ever get everybody turned back to zombies? Well, you think about it, we have a group, and almost like if we have a distance between somewhere. If I get 85%, I get closer. 85% of that, I get closer. Now, if I keep doing 85%, I get closer and closer and closer, but eventually there's going to be a space. I'm going to go 85%, and I'm never going all the way there. I'm only going a fraction. So will this ever equal 0? No, it won't. Now, it's going to get so far down that we might get to, and we can argue, and there is a thing known as in calculus, the limits. As we get so far, the limits are going to be so small that eventually we'll get down to 1 zombie, which is still more than 0. And then if we get rid of 85%, we're not going to have like some guy that's like part zombie laying around. We'll say, okay, that guy's done. Or we just take a shovel to him and kill him off. Then we have no zombies. But just doing 85% will eventually never get there. So what are some similarities and differences you notice between the equations? So no right or wrong answer, but you can just notice here, both of them start out with initial population, and then both of them have a growth or decay rate, and they're all to the x power. All right, what number in the equation impacts whether or not the initial value will increase or decrease over time? So we kind of talked about that growth rate. Look at our formulas there. What number tells us? And what's special about the number? Which number tells us what the initial value is? So what tells us here in our equation? So looking back. All right, so the last problem here is to go through and look at these resources here to help you out to notice some information about them. So using what we learned about exponential growth, what do you think the scientists came? So if we had to act hard, fast, and early, maybe even relate this to the COVID here, and not to get too political or anything like that, but if we had this infection outbreak before it became exponential, if we wanted to act hard, fast, and early, like what should we do? And then what happens when we don't? What if we sit there and debate the facts for a couple days and the growth keeps going? How does that affect? Or if we don't try to, cautiously spread or flatten the curve? What would have happened if we did completely nothing in the beginning of March versus what we did now? So we're going to have a discussion about this as a class to kind of discuss those things. All right, guys, so this is a 2-day assignment. It might take a while, but hopefully you got some things filled out. And when you're in class, you can ask questions, get the other ones. Have a great one. I'll see you guys later.